All right, today we are our last day on Chapter 4 material here, and we're going to see today the one of the most practical applications of this work with symmetry, although we'll see it again in our Chapter 5. We'll use symmetry as well, and then later this semester when we look at transition metal complexes, we'll need some arguments of symmetry as well. So this is an ongoing thread through several topics this semester. But this morning, to round out this last chapter, I want to point out two examples of where symmetry is applied. Okay. One a little more practical than the other. One you've heard of before, although it's the less practical of the two. The concept of chirality, which I believe you discuss in organic chemistry a little bit, right? Well, chirality can be determined, as it turns out, through a lot of the arguments of symmetry that we've been looking at as well. You're used to thinking about chirality as a molecule that has 4 different things bonded to a carbon atom, right? And that's going to lead to chirality. But it turns out that any structure with only the E operation or CN axis, okay, will be chiral. So this would still correctly predict that all the things you learned about in organic chemistry that were chiral are chiral, okay? But it opens up the world a little more broadly. Specifically, the big thing that this has an impact for is transition metal complexes. That may have no carbons in them at all, and yet will act in a chiral fashion, just like what you've really learned about being chiral. So you have to remember, as you learn things, you don't want to commit, you don't want to be sort of like Texas Hold'em all in. The only way that something can be chiral is if it's a carbon atom with 4 different things bonded to it. That's just the way you're being first taught about what chirality is. And then that world's going to open up and expand, all right? And this idea of transition metal complexes, not to get too far ahead of us, but to show you a picture of one of these, the way these will look, a transition metal often can get surrounded in an octahedral fashion, so meaning 6 things around it. And if the things that are bonded to it are sort of these, this one would be looped from the bottom to the back. If they're sort of these wedges or whatever, so they're going to be big things. You call these ligands. Trying not to get too far ahead of myself since this is Chapter 9. We could actually construct the mirror image of this exact same structure here. Okay, the top being now connected to the bottom there, the front still like that, and now the right being connected to the bottom. If you tried to superimpose these two on one another, this connectivity here, would not overlap with this connectivity here. And they'd be the exact same formula, all right? So they'd be a lot like 2 carbon atoms with 4 different things bonded to them. If you attached them in an R or an S sequence, they won't quite overlap. The same thing's going to happen in these transition metal complexes. All right? They can be tricky to look at, though. So it turns out a quick way to figure out if something is chiral, if the only symmetry element you can find is the identity operator, all right, or if the only thing something has is a CN axis. It could be a C2, it could be a C3, okay? It's undefined right now what N is, depends on the molecule. It's going to be chiral as well, all right? And these will interact with light just like you learned about organic compounds as well, all right? A couple years ago in the capstone course, some of the seniors tried to synthesize a chiral transition metal complex and to collect its VCD spectra actually as well. So we didn't quite get a successful completion of that project. So, but that's something that we looked at in that class there. Okay. The other big application of symmetry is the connection to vibrational spectroscopy. Mainly IR and Raman spectroscopy. Right? And I know you've heard of IR spectroscopy because you use it in your organic classes again, and you're used to looking for signature things in an IR spectrum, right, that identify maybe a carbonyl stretch or an OH wide band, okay? So you remember hopefully that there are these distinct features that you can look for in a molecule maybe before and after a reaction that identify some change that has taken place. Is that an accurate, does that ring a bell or whatever? Is that how maybe you've used IR to this point? Okay. Because I honestly don't know. I haven't looked at the syllabus for your organic labs and everything, but that's how I remember using it, even as an undergraduate. All right. And then Raman is a similar technique. Raman is a combination of IR and visible light, as it turns out, which you'll learn a little bit more about in instrumental for those of you who haven't yet taken instrumental, which is most of you. Okay. So now before we can understand really how this predicts IR spectra and what it predicts about IR and Raman spectra, we need to talk a little bit about what are known as the degrees of freedom. Okay. And our book uses water, so I'm going to use the water molecule to help us understand this. Okay. The three atoms in a water molecule, the oxygen, the HA, and the HB, I've just labeled the HA and the HB to keep them separate from one another. Okay. For right now, each atom is able to move right? Physically to move in 3 dimensions. The X, Y, and the Z axis, right? We think of these bonds connecting these atoms together, but we want to remember that a bond is a lot like a spring, all right? It's got some flexibility to it to stretch, okay? And it can also bend. So the water molecule is not at all a rigid little thing. It's undergoing constant twisting and turning and buckling, and its atoms are all moving around and gyrating in space, all right? So for an atom with, or for a molecule, I should say, with n atoms, right, that means a total of 3n motions are possible. Okay? Let's just look at the oxygen atom for a second. It could move in the Z direction. It could move in the X direction, and it could move in the, I'm going to draw it to the back, to the Y direction. Independently of what the oxygen is doing, the hydrogen A could move X, Y, or Z. All right? And if it does, that's going to change the length of that bond, right? And it's going to change the angle of the bond between the 2 hydrogens. All right? And that's where the spectroscopy starts to leak into this, because spectroscopy is measuring, in many cases, the dipole moment of a molecule. So the distribution of the charge, all right? We talked about polar molecules versus nonpolar molecules, all right? So there's the idea of an average, what an average water molecule looks like, but then on any given instant, depending on how much movement is happening, that spread of charge is going to be increased or compressed, and that is going to be detected energetically when the molecule undergoes changes like that. All right. So there's a total of 3n possible motions of this. Okay? Now, if by chance all of the atoms moved in the x direction together, the molecule would literally move in the x direction, right? Or if it all moved in the z direction, the molecule would move in the z direction, right? So that's what's called translation, right? The movement of the molecule. Translation. Movement of the entire molecule in the x, y, or z direction. So of the 3n possible motions, 3 of them always belong to translation. Okay, because you have to account for the fact that this molecule could move. All right. The other interesting possibility is if HA comes this way and HB goes that way and Z doesn't do anything, the molecule is going to spin. It's going to rotate. Okay, so the motions could combine to rotate the molecule in the x, y, or z direction. So there are also 3 of these motions that belong to rotation. Okay, so spinning about the x, y, or z axis. Okay. So if we take the total motions, which are 3n, and we subtract translation, which is 3, and we subtract rotation, which is also 3, okay, what we really end up with is a 3n minus 6. These remaining motions are the vibrational degrees of freedom. So the remaining motions would describe vibrations of the molecule, okay, where it's not necessarily moving, but where it's kind of twisting and bending, all right, where this bond is getting longer, this bond's getting longer, or one's getting longer, one's getting shorter, okay, where the bond angle is changing, but the molecule itself is essentially rooted in the same spot, okay. So that's what the vibrational degrees of freedom are. Vibrations are things like a bond length changing, a bond angle changing. Okay? So those are a couple of examples of that. All right? So this 3n minus 6 is how you predict the number of vibrational degrees of freedom of any molecule, unless it's linear. So if a molecule, MC, is linear, it has 3n minus 5 vibrational degrees of freedom. Okay? It's only 5 in that case because there are only 2 possible rotations for a linear molecule. All right? Not the x and the y direction. There's no rotation really about the z axis then. All right? So you lose one of the rotations, you gain a possible vibration for a linear molecule. All right? Okay. All right. So for water then, n equals 3. There's 3 atoms, right? Which means that there are 3n minus 6, or 3 vibrations. Okay, 3 possible vibrations. So the trick then is to figure out what are those vibrations and how do we determine them. Okay, so how do we determine the vibrations of a molecule? Okay. In other words, I'm literally trying to figure out what can the water molecule do? how can it behave? Right? All right. So there's a cool way to do this. For a tiny water molecule, on the one hand, you could just kind of grunt your way through it. You could brute force kind of figure out what are the possible things you could do with a molecule, right? But that's not going to help you then when you get to like a larger molecule, all right? So here again, we try to train ourselves on smaller pieces, smaller molecules. Let's develop a system that we could, understand how that system is working on a smaller one and then gain that trust that it works, so therefore we can apply it to a larger molecule, all right? And what we want to do is use symmetry to develop what's called the total reducible representation. Talked a little bit about this last class, I think, how we would generate this. The total reducible representation of a molecule accounts for all the atomic motions. Okay. So what you do is you place an XYZ coordinate axis on each atom of the molecule that you're looking at. Okay. And then you perform each symmetry operation, considering how the x, y, and z vectors are impacted. Okay? If an atom moves, not the vectors, if an atom moves, okay, during the operation, it contributes 0 to the total reducible rep. Okay? Because none of its vectors are going to be in the same position that they originally were. All right? If an atom stays in the same position, it contributes to the total reducible rep. But here's how. Okay? For every time you, this is just as an example, if x transforms to x, that adds 1 to the total reducible rep, the TRR. If x transforms to negative x, because maybe it rotated 180 degrees, that's going to add negative 1 to the total reducible rep. If x transforms to y or z, to one of the other coordinates, that adds 0 to the total reducible rep. There's one tricky case. If x transforms to, I'll even write this out. If x transforms to something between, okay, something between x and y, or z, depending on the rotation or the angle, okay, a different value may be added. I may show you one. Okay, I may show you one of those as an example. Usually we're going to see 180s and 90s and keep life simple. All right. But if you had a C3, because they're not that uncommon, luckily a C3, we could show that I'll show you it equals 0. Okay. Okay, so for example then, we have to continue this. Okay? Water, H2O, is in the C2V point group. Okay? So again, suppose that our water molecule, that each atom had an X, Y, Z on it. Okay? Z always aligns with the highest Cn. That dictates what the z-axis is for the entire molecule. X, okay, is coincident with the plane of the molecule, if there is one. Okay? So water being a flat molecule, right? We're going to try to get as many atoms in the XZ plane. That's this plane, so that means this is the X dimension then. All right? And then Y would be the remaining, the remaining perpendicular one. All right? So that's how you decide what Z is. That's the most important. And then the X and the Y. Okay? All right. So water is in that C2V point group, so we want to write out the character table for C2V. All right? We have E, C2. We have a sigma XZ and a sigma YZ, called the sigma prime, right? Okay. Did those in the right order. I just want to make sure I had those in the right order. Okay. So right now we're going to generate a reducible, what's called a reducible representation, the total reducible representation. There are 9 little vectors in play right now. You see them, right? Because we put an X, a Y, and a Z axis on each of those. This is where your fingers come in really handy. People laugh every year, but you know, this is happening, you know, in classrooms around the country. Okay, it's very convenient. All right. So when we perform the E operation, we don't move any of these atoms, right? They're all in exactly the same spot. Nor would any of them rotate or twist around or do anything, right? Or reflect. They're all identical. So every one of these 3 coordinate vectors, as we've got, Z, X, and Y, looks identical after the operation and before. So the E operation, when we perform it, 9 gets a contribution of 9. All of the coordinate vectors are identical after it. Okay? Really, E should always be, by the way, 3n. It's your total degrees of freedom. Total motions is what that's describing. Okay? All right. When we perform the C2 operation, okay, after the C2, our H, I had earlier HA on the left and HB on the right, right? So now our HA is on the right and our HB is on the left. These two do not contribute because they have moved. So we don't have to worry about them now. So now we just need to worry about what is our oxygen doing. Its Z is still up, its X now is there, and its Y is now here. Right? This axis that was up here, okay, if we perform a C2, what happens? It rotates 180 degrees. There we go. I didn't go 180. Okay? So it goes from that to that. All right? Although I have it I actually have it. I have it starting here. Sorry, my wrist broke and I can't quite rotate it properly anymore. All right. So it looks more like that. There we go. That's what it should look like. Okay. This looks like, well, no, wait. That's what we have right now. So then my middle is out in front of you. There we go. Okay. What's the result of that? Well, the Z became Z. It's still where it was. So this is just an example using X, right? But the Z vector stayed where it was. So that's going to add 1 to the reducible representation. The Y vector went from being out back to being out front. It went from the, if we call that the positive Y direction, it went to the negative Y direction. So that's going to contribute -1 to our representation. And our X, if that was the positive direction, now it's pointing this direction, is also X to negative X, so that's going to contribute -1. So we just add these three numbers up. 1 minus 1 minus 1, and we get a -1. Again, that's coming from the oxygen, all right? And we ignored the two hydrogens because they moved. All right? Super simple. That's the first thing you want to look for. Just get rid of the stuff that moved and only worry about the atoms that stayed in place, although their coordinate vectors may have changed. Okay? All right, sigma xz, plane of the molecule. All right? So if I try to draw it afterwards, sigma xz, right? Our atoms are back in their original places, HA and HB. They didn't move. So all three atoms are going to contribute potentially. If we're reflecting xz, we're reflecting front to back. So the z didn't change, right? On all of these, the z stayed the same. The x didn't change. But the y went from pointing backwards to pointing out front. Okay? So z went to z, x went to x, but y went to -y. So that's +1 for z, +1 for x, -1 for y. Okay? Our coordinate system went from looking like this, essentially, to looking like that. So these two stayed the same. This one changed. So any given atom has a total contribution of 1, but all three atoms did the same thing. So we could just sum that up and get 3 as the total. Okay. Any questions on it? Getting it or not? Okay. All right. Now, go ahead.
How did you get -1 for C2 when you said you added up the three negatives on the X, Y, and Z plane? For C2.
For C2. Okay, again, ignore these right here. Okay? And so Z is +1, but Y and X are -1 each. So it's 1, -1, -1. It is -1, -1, +1.
All three minuses.
Oh, this is plus. Yes, there. Sorry. Okay. Josh?
So with the planes, when you add them up, it's only if you add up how many contribute, not like the actual numbers. So like when you one because like you have the Z contributing 1, the X contributing 1, the Y contributing 1. So that wouldn't be 1 because if you add them all.
It is 1. You're right. It is 1 for the oxygen. But we also have to do that for the hydrogen, which is going to have a net value of 1. And the other hydrogen is going to have a net value of +1 as well. So for every atom that doesn't move, they're all going to behave the same way. All right? And so if you figure out one atom, you just have to multiply it by the number of atoms. All right? I mean, I could have written out all of these. Then I'd have 9 numbers. 6 of them would be, +1s, and 3 would be -1s. They would add to 3. Okay? All right. Let's look at the other reflection. The other reflection is the YZ plane. The left side reflects to the right side. So HA and HB, after the reflection, switch places. So they've, again, literally moved, just like they did in the C2. So we're going to ignore them. And all we have to worry about is the oxygen. Z is unaffected. X gets reflected. And Y stays the same. So Z stayed as Z. So that's a +1. Y stayed as Y. That's a +1. And X became negative X. So that's a -1. So now again, the sum is 1, 2, -1, so we're back down to 1. But this time only one atom stayed unmoved. So the total for the molecule is a net value of 1 this time. Okay? So now there's some patterns here. Every C2 is always going to contribute. Any atom that doesn't move is going to contribute -1. Right? So you just have to figure out how many atoms don't move. Okay? It would only be atoms right on the C2 axis. Every mirror plane, regardless of whether it's horizontal or not horizontal or vertical, every vertical mirror plane, regardless of whether the plane of the molecule or perpendicular like this one, is going to contribute +1 per atom. The difference here was 3 atoms did not move in sigma xz, and 1 atom did not move in sigma yz. All right? And so it's not, students sometimes think, oh man, I have to do all this work every time. If you pay attention, you figure out that pattern really quickly. Wait, mirror planes act the same way. C2s always act the same way. It's just a matter of recognizing how many atoms you have to apply that to. Okay? And then you get a lot quicker at analyzing these. Okay? All right, so what we just developed there was what's known as the total reducible representation of the water molecule. So that gamma there describes all of the activity of the water molecule when it moves. It's all encapsulated in there. Okay? So this gamma total, though, so here's now where the next powerful element comes in, is some combination of the irreducible representations of the point group of the molecule. And we can reduce gamma total to find the components. Okay. So here's how we reduce. I showed you this, I believe, last time as well, but so let's put our gamma total over here again. It was 9, -1, 3, 1. What we need is the character table of the point group of the molecule. All right, so it has 4 irreducible representations, A1, A2, B1, and B2. Right? And going down, 1, 1, 1, 1, 1, 1, -1, -1, 1, -1, 1, -1, and the last column, 1, -1, -1, 1. The order of this is 4, total number of operations, 1E, 1C2, 1 sigma xz, 1 sigma yz. Okay. I think I showed you this formula last time. The way to figure out the number of A1s is to take 1 over the order, so 1/4, and then you're doing this repetitive coefficient of the operation times the total reducible representation value times the reducible representation value. All right? So in this case, that's 1 times 9 times 1 plus 1 times negative 1 times 1. Okay? Plus 1 times 3 times 1 plus 1 times 1 times 1. And this has to come out to be some integer value, right? So it's 9 minus 1, 8, plus 3, 11, plus 1, 12, divided by 4, means that there are three motions, 3 of the activities of the water molecule are described by A1 symmetry. A1 symmetry is all symmetric, right? It's all plus 1s. All right, so that's what's called an all symmetric. Okay. And now if we repeat this for A2, what do we get? 1/4. The only thing that changes, here's where it gets quick, is to just change out these last ones. That's going to be 9. Again, minus 1. This is going to be minus 3, minus 1. So 9, 8, 5, 4 divided by 4. So there's 1 A2 motion. How many B1s? 1/4 of 9. The sign of the second term would change, plus 1. The sign of the third term goes back to its original value, plus 3. The sign of the last term is negative, unlike the original. I'm always going back to the original, the all symmetric, all right, to get this quick thing. So that's 10, 13, minus 1, 12. So there are 3 B1s. And then our B2, 1/4 of 9 plus 1. Okay. Sign changes, minus 3, and then plus 1. So that's 9, 10, 7, 8, divided by 4, 2 B2s. So our total reducible representation is described as the sum of 3 A1 modes, A2, 3 B1 modes, and 2 B2s. Okay? And you should just double check, does that add up to your 9 total degrees of freedom? 3, 4, 5, 6, 7, 8, 9. All right, so you got them all accounted for. Okay. So now what are these? Okay, here's where your handout starts to come into play. All right, on the handout that I gave you there, where you could see the character table, kind of like what we just had right here. I did not draw out some information that's in the far right-hand columns of the character table. All right, the last 2 columns, although we're actually interested in right now the first of those 2 columns there. So I'm going to just erase my A1s, right? In the next column here, there was the Z, the letter Z next to A1. There was RZ next to A2. There was X and RY next to B1, and Y and RX next to B2. Okay. What these tell us is translation in the Z direction is essentially described by this type of symmetry. This is how the molecule is transformed or looks. Translation in the X direction is essentially described by this change to the molecule in terms of its position vectors. Okay? Translation in the Y is described by the B2. Right? So out of our total here, I don't want to work too far away, so I'm going to come right here. So again, our gamma total was 3A1 plus A2 plus 3B1 plus 2B2. But we could subtract from that an A1, a B1, and a B2. These are the translations of the molecule. All right? That's what the letters X, Y, and Z. Why did I pick A1? Because that's what Z is described by. Okay? B1 is describing translation in the X. B2 is describing translation in the Y. So this is always present in these character tables, these letters. Okay? The R's describe the rotational activities of the molecule, right? So earlier, right, we said atoms can do all these things. Sometimes the motions line up to give us translation. When that happens, how all these vectors change is described by these three irreducible representations. And if they rotate, here's your rotations about your X, Y, and Z axes. So we could subtract them if they're present as well. So we had an A2. So we could subtract A2. All right. We have another B1 and another B2. Oops, that should all be minuses. So if we get rid of all of these, that's both of our B2s that are gone. Two of our B1s are gone. Our A2 is gone, and 1. So what we have left belonging to our vibrations are 2 A1s and a B1. So I've called this now gamma vibe, right? So these are the vibrations of the molecule. Again, A1 is what you commonly hear called the all symmetric, because it's all plus ones, right? And so there are two, what this is telling you is there are two things that water does with regards to vibration that are entirely symmetric. In organic, you may have heard of them being called the symmetric stretch. Does that term ever sound familiar to you? You ever heard something like that? No? Okay, maybe not then. All right. All right. But anyway, there's this thing that water can do where its two bonds stretch at the exact same time. And this is what the water molecule looks like. That would be called a symmetric stretch. All right? And then there is the symmetric bend, where the two atoms move in and out together at exactly the same time. Okay? Like that. The other vibration that water has is called the anti-symmetric stretch. Okay? In, out, in, out, in, out. One in, one out. One in, one out. Okay? That's the other way the other vibrational activity. That one, the anti-symmetric stretch, is described by the B down here, the B1. All right? So how the water molecule is changing is described there. All right? So what we've done here is we've developed the total behavior of the water molecule. All right? And then we backed out we reduced that first, and then we backed out what modes corresponded to translation, okay, because every character table is going to tell us, right, how Z transforms for any molecule that's part of this point group, all right. The Z coordinate transforms like this. The X translation, would look like this. Okay, and so on. And we backed out then the rotations, so what's left are the vibrations. Okay? Now here's where we get a connection then to IR spectroscopy. Okay? Just because something vibrates doesn't mean it will be detected in an IR spectrum. All right? So if a vibration changes the dipole moment of a molecule, it will be detected in IR spectroscopy. Okay? So if something the molecule does changes the distribution of its charge and the separation and distribution of its charge, that's going to be detected in an IR spectrum. All right? How does symmetry tell us that? So if, okay, well, the shortcut for us to figure this out is if a vibrational mode, okay, shares the symmetry of X, Y, or Z, okay, it will result in IR activity. Okay? So for water, both A1 and B1 are IR active because A1 has Z, right? Or A1 transforms, I should say, Z, and B1 transforms, that's B1X. Okay? So not only will this column help us back out from the total degrees of freedom of the molecule the things that belong to motion in the X, Y, and Z direction, okay? But it will also help us identify, of the remaining vibrations, which ones, if any, are IR active. All right? And the three motions that I just did a second ago, the symmetric stretch, if the bonds both come out and come back in, right? If the hydrogens get out further away, that is separating the charge. The dipole moment is getting larger and larger, okay? And so that means it's IR active, okay? And if the molecule is bending in like this, that's also redistributing the charge, okay? And then if we're going this way, now you're getting more lopsided as well. So these are all IR active, okay? Because it changes the dipole moment. Okay? Now there's another type of spectroscopy called Raman Spectroscopy, as I mentioned earlier, that most of you probably have not worked with yet. Raman is similar, okay, in that it does use IR, but it combines IR and visible, I believe. Okay. So a vibrational mode is Raman active. So if a vibrational mode has symmetry that matches what we call the symmetries of the D orbitals, which are the dxy, the dxz, the dyz, the dz squared, and the dx squared minus y squared. Those are the 5 names of the D orbitals, okay? Based on their shapes is really where those come from. So if it has symmetry that matches the symmetry of the D orbitals or a linear combination of them, it's a little rare, but it's part of the thing, okay? It will be Raman active. So the last column in the character table is where you see, again, if you look at the handout that I gave you, the far right column, we see, if I erase a little bit more of my example here now, but you could just look at it on your piece of paper, we see next to A1, x squared, y squared, z squared. Then we see xy, xz, and yz. All right. So A1 describes the symmetry of the dz squared orbital. And B1 describes the symmetry of the xz, the dxz orbital. So not only are those two going to be detectable in an IR spectrum, but they're going to be detectable in a Raman spectrum. Okay? So you might think, well, who cares? If we see them in one, why would you see them in the other? Because if you're trying to identify the structure of a molecule, you want as many ways to see it as possible or visualize it as possible. All right. The book will give you some examples of considering like some isomer of a compound that you made. All right. Where this all leads is if you're not sure what structure a molecule has, you perform this analysis. Okay, so you assume it has the structure that you think it might have. Perform this analysis and it'll predict how many IR and Raman bands you would see. And then think of another configuration of the molecule and perform that analysis. It may predict a different number of IR bands or Raman bands. So if one predicts 3 IR and 3 Raman, and one predicts 2 IR and 1 Raman, then you collect your IR and Raman spectrum, and you figure out which structure you have based on which number of bands you see. Okay, so you'll have sort of theory agreeing with the experimental predictions that you'd have then. Okay, all right. Another way that this gets used pretty classically is with coordination complexes. And a sort of a quicker, easier way to accomplish this as a shortcut is if you had a transition metal that was coordinated with carbon monoxides. Because this carbon monoxide is like a spring. And so it can stretch back and forth. And so there are 6 carbon monoxides, in this case, pointing in. So we can generate a reducible representation for just the CO stretches, rather than not an entire X, Y, Z analysis like we just did on water. So this is a little bit of a shortcut. The only thing that's going to possibly be Raman or IR active in this molecule is going to be this stretching of these carbon monoxides. All right? Now in this case there'd be no difference because they're all 6. But if I took 2 of these away, we could have potentially a planar molecule. Oh, we know that's the way it would be, right? But maybe we could have some other configuration. And playing around with all the different possibilities for where 4 of those carbon monoxides could be would lead to different predictions of how many IR how many IRs you would get. All right. So this would be pretty tricky. This is tetrahedral. It would be a really high value. So if we wanted to develop this, we would. No, I'm sorry. This isn't tetrahedral. This is octahedral. Okay. So I need the octahedral character table. All the character tables that you guys would ever need are in the back of your book, by the way. Okay. So if I found the octahedral character table, be OH. It's huge. It's got tons of things to it. All right. But E, 8 C3s, okay. Maybe this isn't octahedral. How does that have a C3? It's got C4. Oh, they're there, C4s. This isn't OH, this is just O, I think, okay? Anyway, what I just wanted to show you is that the gamma for these COs would be like 6, okay? 6 of these, because none of them would move on the E. And then if you had a C4, when you rotate this molecule that way, well, these 4 all move, but these 2 don't, right? So the 2 that didn't move contribute the 2 that you have there, right? And if you had a C2, well, everything in the plane, again, would move, right? And then if you had a reflection, if it was the plane of the molecule, these 4 wouldn't move. So rather than looking at X, Y, and Z, all right, in transition metal complexes, it's the carbon monoxides that lead to the potential spectroscopy, the IR activity. And so you could just zero in on that single stretch. Okay? All right. The back of the handout that I gave you guys repeats the analysis that we did for water, but for XCF4. So it kind of goes through showing you what it doesn't do the reducing like we did out for water here, but it does show you what the total would be and then what those are all connected to. All right? Okay, I need your homework set. Looks like this is it. All right, so tonight's homework is going to be a lot of practice on generating these total reducible representations and then reducing some of them as well. All right? Okay. So you'll generate these total reducible representations, and then you'll break them down much like we just did with the water molecule. And then on the back, the IOF5 structure is missing, I just noticed. Okay? For some reason my ChemDraw structures don't always print out. Sorry. So for number 4, the IOF5, I is central to the molecule, O double bond at the top, and F also axial, and then the other 4 Fs are in this configuration here. So it's like an octahedral geometry there with oxygen at the top. All right, so that's the IOF5, which puts this in the C4V point group that we would have. Okay? All right. That's all I have for today. Again, Thursday, I can review some of this. We're also reviewing on Thursday for our first exam, which is 1 week from today, on chapters 2, 3, and 4. All right? So be ready with questions, and I'll see you then.